let's talk about these situations where we do find an exponent outside of parentheses. And again, we're going to build our way up based on things that we already know. Let's use this for an example. 2 to the third to the fourth power. Let's look at this in expanded form, but the way that we're going to expand it is by thinking about this exponent on the outside as our actual exponent. This exponent of 4 tells us that something is being multiplied again over and over for a total of 4 times. This exponent, since it's on a set of parentheses, it tells us that it is this entire quantity in parentheses that is multiplied over and over. It's 2 to the third that is acting like our base, and the exponent is 4. So we have 2 to the third times 2 to the third times 2 to the third times 2 to the third, total of 4 times. At this point, we can definitely think expanded more if you want. 2 times 2 times 2, 2 times 2 times 2, and so on. But let's not do that. We have done a lot of work on this situation that we were just looking at about when we have the same base and it's all multiplied together. We know that we can just add those exponents up. 3 plus 3 is 6, 3 more is 9, and then 3 more to make 12. If we thought about expanded form, we would see how many 2's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all multiplied together for this 2 to the 12th. So do we begin to see another pattern here in terms of what an exponent outside of parentheses does, how that would change the exponent inside parentheses? Let's look at another example with variables. How about x to the fifth to the third power? I want to write it in expanded form again. This is x to the fifth multiplied over and over 3 times. And now we know all multiplication. We can add these exponents. 5 plus 5 is 10. 10 plus 5, 15. Do we have the same pattern at work in both of these examples? It looks like we do, that it's multiply these exponents. But again, it's useful for us to see why it is that we multiply these, because this exponent of 3 is telling us that we have x to the fifth once, twice, 3 times. So we have 5 3 times. Do 5 times 3 to come up with how many total x's we would have in this multiplication. Now, I don't want you to always focus on expanded form. If you are sitting there thinking, I got it, man, I know what to do when I see exponent outside parentheses, I multiply it in, I don't need you to always see it in expanded form. I think it's a helpful way for us to see how and why things work, but definitely it's these patterns that we want to begin to use in the future that helps us do these problems in a more efficient way. Let's take a moment here and talk about, could we state this rule using all variables in this very common way of stating rules? If we had some expression, a to the power of m, and that was in parentheses and it had an exponent of n, what would we say this equals? If our base is a, we know we multiply those two numbers together. A to the power of m times n. Those two numbers multiplied together would be our new exponent over here. Let's go to the next level a little bit and look at this example, 3x squared to the power of 4. It's to the next level because we have a couple of different bases in here. We have a 3 and we have an x. So what does this exponent do when we have several pieces inside our set of parentheses? Let's look expanded form again. This is going to be 3x squared multiplied over and over again 4 times. Now it's all multiplication, so let's pick things out in the order that we like. Let's pull out 3 times 3 times 3 times 3, and let's write it as 3 to the fourth. We know that can be 81, but let's leave it for now, 3 to the fourth. Now let's look at x squared, x squared, x squared, x squared. That is x squared to the fourth power. So 3x squared all to the power of 4, it led us to that we have 3 to the fourth, and we have x squared to the fourth. Let's do a little bit more simplifying here. We developed that rule about exponent outside of parentheses should be multiplied to that exponent inside parentheses. That would give us x to the eighth. For now, we've got 3 to the fourth. Let's go ahead and turn that right now into 81x to the eighth. That would be the answer I like for how to simplify this expression. But I do want to point out what exactly is going on. I thought we had a rule here that we could take an exponent and multiply it to the exponent inside parentheses. That 4 times 2 gave us x to the eighth. But how does 3 just get the 3 to the fourth? Well, if you're saying we know that's an exponent of 1, now our multiplication rule, it still works perfectly. 4 times 1 equals 4. We won't always put the 1 there. We can know that if there's no exponent, we just take this one outside of parentheses, and it now is the exponent for that base if it doesn't have an exponent. But if we like to think multiply everything, multiply that exponent into other exponents, just know that that 3 has an exponent of 1, and our multiplication rule still works. 4 times 2 will give us our exponent of the x8, and 4 times 1 will give us the exponent of the 3. We could state this one with another rule here. What if we had some expression a times b, and it was all to the power of m? What would it look like once we take that m and put it to each of those pieces? The exponent outside of parentheses belongs to every single base that we have inside parentheses. That exponent of 4, we had to make sure that we applied it to the x squared, and we had to make sure that we applied it to the 3. That's the gist here is exponent outside of parentheses, we have to make sure it works on every base inside the parentheses. Let's continue with a few more examples. This one is different because we have a fraction inside, but our rules are going to apply the very same way. If you've started to think that an exponent outside of parentheses needs to somehow work on every part inside parentheses, that's absolutely correct. Let's take a look at expanded form just to show why. This would be 2x over y as the base. All of this to the third power. I have it written out 3 times. Let's collect these. Now, if you're saying, okay, now we have division in here, do those rules still work about I can multiply and pick things out in any order? The short answer is absolutely yes, but we have to make sure that if we're taking things from the numerator, from the top part of the fraction, that they all belong together on the top. And when we put together things that are on the bottom of the fraction, the denominator, those need to stay in the denominator. And we will get to a point where we see how we can work the numerator and the denominator together. But for now, what you should think always is, for now, always, let's go with that. What you should think for now is that we always keep the tops on the tops and the bottoms on the bottoms, to use the most technical terminology I could come up with. But let's keep going. Where I'm going is this. 2 times 2 times 2. So we have 3 2's on top. We have x times x times x. We have 3 x's on top. We have y times y times y. We have 3 y's on the bottom in that denominator. We still want to see that it is true. The exponent outside of parentheses needs to work on every base inside parentheses. We also know that if these don't start with an exponent, we can either say this exponent outside of parentheses, it goes there, or if we say, the rule is actually that this exponent outside of parentheses is multiplied to each exponent inside of parentheses, then we would know that there are exponents of 1 on each of these, on the 2, on the x, on the y. I did a little cleanup here. 2 to the third equals 8. That's a nice looking answer. I think we've got to come back here. So this was the example we looked at before where you did it without that exponent of 2. And we did it correctly where we said just go ahead and multiply the 8 times the negative 2. and then we put together x to the third with x to the fourth, and we brought down the y, and then I made this big deal about if there's an exponent there, we have to take care of that first. So here's our example where we're going to finally get some closure to this problem. Our first move is take this exponent outside of parentheses and work it into each base inside the parentheses. That makes our 8 now 8 to the power of 2. When we already have an exponent there, we know that that's a multiply. This is 2 times 3, 6. Okay, that's how we handle this exponent outside of parentheses. We work it in. Now we're looking at 8 to the power of 2, x to the power of 6. This set of parentheses is a-okay because we had no exponent back here for us to work in. And now we are back to that situation where we can multiply our numbers together and begin to put these variables together. No more exponents outside parentheses. Okay? 8 to the power of 2 is 64, and then the 64 times negative 2 is negative 128. We can put together x to the 6th with x to the 4th, x to the 10th. And finally, we have just the 1y that we'll bring down. And there's our answer. Okay? Exponent outside of parentheses is what we always will start with. Once we have worked that in, then we can begin to multiply our numbers together and collect like bases, the x's put together and so on. Here's one for you to try. I know you're anxious to try one for yourself, so pause the video and try this. It's going to be some similar steps to what we did here, but notice that both sets of parentheses have an exponent that we need to work in. Okay, so pause the video and try it, and then restart the video and we'll go through the answer together. First move, on this set of parentheses, an exponent of 2 is being worked into each of these bases. That will give us 3 to the power of 2. It'll make this x to the power of 4 and y to the power of 2. Then I'll move over here. This is 2 to the third power and y to the 6th power. Remember, no exponent, then it just goes there, makes it 2 to the third. If there already is an exponent, we must multiply. 3 times 2, 6. And again, if it's your preference to, at the start of this problem, say, this is 3 to the power of 1, this is y to the power of 1, this is 2 to the power of 1, and then when we work the exponent in, we just multiply to every exponent. I think that's great. If that works for you, then that's great. Do that. If it works, we do it. That's really the number one rule out of all of this. Whatever works, we do. If it keeps you accurate, you do it. Well, let's continue here. No more exponents outside of parentheses. I even just dropped those parentheses altogether once I worked that exponent in. Let's multiply the numbers. 3 squared is 9. 2 to the third is 8. Careful there, not 6. That we know that that's 2 times 2 times 2. So 2 times 2, 4. 4 times 2, 8. Let's multiply the 9 times 8, 72. There's our coefficient. Okay, now we have to put our variables together. We do have an x to the 4th here, but no other x to the 4ths. Or no other x's at all. Just that x to the 4th, bring that down. We're good. And then y's. We have y to the 2nd and y to the 6th. And we know once we're looking at this multiplication that we add those exponents. Again, there's no way around that. It's going to be funky. And even into the future, we see this kind of relationship more where we're saying, how is it that I'm looking at a multiplication problem, but what I'm doing is adding? And it really is because of what exponents tell us. Exponents tell us how many multiplications are going on. So if I multiply more to that, I'm really just adding more onto the list. It's something that you want to make sure that you're kind of always aware of, that we don't slip into something incorrect. Anywho, y to the 2nd with y to the 6th together, y to the 8th. There's our answer for this problem.